Hi, my name is Jennifer Kennedy. I'm a PhD candidate in geographical sciences at the University of Maryland in College Park, and I'm supported by NCASM. So my primary research involves looking at the impact of climate change and particularly drought. So it's a nice lining up with the previous speaker on agricultural land uses, but also working to develop metrics that can translate predictive weather and climate information into decision support tools. So I'm going to be talking today about applying NOAA climate data to predict days suitable for fieldwork, which is a metric used for agricultural planning. And I know that agriculture is a little bit outside the primary NOAA domain, but I think that this process of translating the short-term and seasonal predictions into usable information for decision-making is very much in line with the larger NOAA objectives. And my co-authors for this research are Dr. Jinzhong Liang and Dr. Chao Sun, both also at the University of Maryland. So we all know, and as we saw in the previous presentation, agriculture and food production systems are extremely vulnerable to weather conditions. And the food system is likely to become more and more stressed in the future as we see increases in both climate extremes and climate variability. So it's really important that we continue improving predictive capacity, but at the same time, it's not enough to create good predictions, as hard as that is. We also have to work with communities to make sure the information is delivered and delivered in useful and usable ways. So you can have the best, coupled climate hydrology crop model in the world, but for it to be useful for decision making, farmers need to be able to access the results. And more than that, the information needs to be targeted towards the types of decisions that they're trying to make. It needs to be available when they are making those decisions, not 2 years after they made the decisions. And it needs to be at decision relevant scales. And while there's a lot of highly sophisticated farm planning software available to farmers in the US, right now, most products are not directly linked to predictive weather or climate information. So there's this, huge gap in terms of, NOAA's putting out increasingly successful seasonal forecasts, especially with the S2S prediction efforts. But a lot of those are not getting linked into the decision-making tools farmers are currently using. So I'm currently affiliated with a group that's trying to address this gap through DAWN, the Dashboard for Agricultural Water Use and Nutrient Management. And we've used a little bit of poetic license with that acronym. So DAWN is an interdisciplinary project led by Dr. Jinzhong Liang at the University of Maryland. And our goal is to remove some of the separation between the scientific and agricultural communities by translating the best forecasts and outlooks into agriculturally relevant metrics at the spatial and temporal scales needed and requested by farmers in the US and corn and cotton belts. So we're working with a group of scientists, modelers, extension experts, and farmers. So you can see here a map of our focus area and partner locations. The green circles represent farms in our network, and the red stars are partner universities. And so we're working to co-create and refine a suite of modeling-based decision tools. You can find more information if you're interested on the website or Twitter page. It's a really cool project targeted towards making climate predictions accessible. So through our discussions with farmer and extension partners, we spend a lot of time asking about information needs. And one of the most commonly requested metrics is days suitable for fieldwork, or DSFW. So when we talk about food security or weather impacts on crops, we often sort of default to the biophysical factors. Extreme heat decreases yield, or drought, as we just saw, causes crop loss. But there's also a logistical component to consider, which is, can farmers go out onto the field to do the necessary field work? Farm labor, which can be everything from planting, harvesting, fertilizing, pesticide application. All of these activities have optimal windows for completion depending on the specific crop in the area. And it doesn't matter how perfect the growing conditions are if the ground is too muddy to get a tractor out onto the field. We saw this a couple years ago where just, all Western planting was extremely delayed because of rain. And then conditions for the rest of the year were mostly fine, but everything was so delayed that we saw major crop yield impacts throughout the rest of the season. So having a sense of the number of working days allows farmers to make management and timing decisions about the amount and type of seeds to plant, or the number of people to hire in different seasons, or how much machines to rent. So, and typically fieldwork planning tends to rely on historical patterns. So on the left here, you can see the 25-year historical distribution of working days in a few sample states. And you can see there's very different patterns across the states, which are largely due to differences in climate, but also local cropping needs. Some of these some of the states are doing cotton, some of them are doing corn, some of them are doing wheat. And obviously there's a huge amount of scatter from year to year. So typically the planning process uses something like the chart on the right, which I took from a Missouri Extension training document for farmers. So as a farmer, you decide how much risk you want to accept. Then you look at the associated number of field work days, and then you plan accordingly. So here we have DSFW on the x-axis and probability on the y-axis. And we can assume that about 50% of the time, Missouri is likely to have at least 27 working days available between April and May. So based on that, you can make farm decisions to make sure you have enough materials, equipment, and labor to get the planting done in that allotted 27 days. The problem with this, obviously, is that climate change is altering the distribution of weather conditions, which means that historical norms will be less and less reliable in the future. For some reason, it doesn't want to go forward. Okay, so what I've been working on here is a project to link the climate data to historical DSFW records in order to build a tool that can use NOAA forecasts and outlooks to predict working days across the continental US. And the tool will be integrated into the Dawn dashboard and will allow farmers to see projected working days in their region over the timescales that they are interested in. So basically translating those forecasts into directly decision relevant information. So for example, the farmers could focus in on the corn planting period or the wheat harvesting period and see the number of projected working days in their region over the time that they would normally allocate for this. So the USDA tracks working days going back to about 1995. They actually do it before it, but it's in non-searchable PDFs, which is not very useful for my purposes. And the data are collected locally from agricultural reporters throughout each state, and then averaged into a single weekly number per state. You can see an example week of that on the left. So even though the data is collected more locally, the aggregate number is unfortunately the only metric that's available. So I compared this with NCEP's NLDAS reanalysis data. There's an example of 1 week of soil moisture for this on the right, or sorry, 1 day of soil moisture. And I did this for a number of variables: soil moisture, precipitation, temperature, and snow cover. So the biggest barrier in this analysis is the lack of spatially discrete working day data. You can see there's a lot of regional variability in soil moisture that's going to be completely lost if we just aggregate everything to the state level to compare it with the days suitable for work data. So to try and capture the spatial variability, despite being only able to validate at the state level, I used an iterative threshold optimization method. I aggregated the gridded climate data to the daily county level in order to approximate the underlying conditions that would have been reported to the USDA from the different reporting locations across each state. Then I set a threshold for each variable that defined whether or not the day was suitable, calculated the number of suitable days per country, or sorry, per county. And we found that the weekly average per state, and then compared it to the observed DSFW. And then finally, I iteratively adjusted the threshold to find the best fit for each variable in each state. And so the reason I set different thresholds per state was to account for the different crop types, soil types, and infrastructure, all of which influence workability decisions. A day that's workable in one state for one crop might not be workable in a different state for a different crop. So I developed the thresholds using 2/3 of the data as a training set and then evaluated its performance over the remaining 9 years. And this whole thing was from 1995 to 2020. So I found that overall soil wetness was the strongest driver of workability, with precipitation a close second. So the figure on the top here shows the primary driver in each state. Blue represents, suggests that the decrease in error was more due to wetness. Red represents a larger decrease due to precipitation. You can see there's a lot of red over there for the Western states, whereas the Southeastern states are mostly driven by soil moisture. Overall, using a combination of temperature and precipitation gave the best results. And in several states, you can see these in the bottom graph, adding a snow cover variable slightly increased skill. Unsurprisingly, these were mostly states up to the north. I also looked at temperature, but its impact was negligible, so it was not included in the final model. Okay, so the current model is quite successful at estimating the number of working days using reanalysis data. So here we have 2 sample states across 3 years. Illinois is on the top and Nebraska is on the bottom. And the blue line represents observed working days over time for these 3 years, and the dotted orange line represents our model predictions. So you can see that overall, the model captures the bulk of the variability, including at the beginning and the end of the season, which are the most critical for fieldwork and typically also the most uncertain. So you can see that it gets a little off track in places, especially Nebraska in the middle of 2012, which was actually a drought period, which I suspect contributed to that. But in general, the fit is pretty good. So zooming back out over the US, here we have root mean square error by state. The map on the top shows a statistical seasonal fit model where we simply use the historical mean per week of the year to estimate working days. And this was meant to approximate the traditional method of basing my expectations on historical occurrences. So the errors here run from about 1 to 2 days per week, depending on the state. And at the bottom, this is our MSI based on our new threshold model. And you can see there's a notable improvement in performance. The errors are reduced to about 0.5 to 1.5 days per week. And skill varied geographically. The highest skill was definitely in the South and the West, and the lowest in the Northern Midwest, possibly still related to frozen ground issues, which we're not fully accounting for. So overall, I'll wrap up. This method is looking really promising. It shows the potential for using seasonal forecasts to add value to current farm planning tools. We're currently working to develop a predictive version using CFS data, which wasn't quite ready for today's presentation, but the goal is to integrate that into the Dawn decision support framework and make it available to farmers. So we hope that this will address an important gap in the information currently available. And since it's such a widely requested item, that it will help increase interest in the use of other predictive climate and weather tools as well. So my research today has been sort of supported by NOAA, obviously, as well as the NSF and the USDA. I'm very grateful to all of them, and especially to NCASM, which is very much the reason I'm working on climate science at all. So my email is on the slide if you have any questions or comments that don't fit into today's session. And thank you very much for your time.
Thanks. We have time for a couple of questions people have. No? Okay.
Listener?
Yeah, go ahead.
So, so the temperature wasn't useful, but that you thought that you might have been seeing things related to frozen ground. Can you bring in a history of the temperature or some idea to help you get that information?
I'm sorry, I'm having a little trouble hearing through the, but I think you were asking about the frozen ground.
Yes, whether the temperature or whether integrated temperature could be a good predictor for that.
Yeah, so I tried using a just air temperature factor, which did not have any correlation, even when I just isolated it to the colder northern states. I have not tried, I would like to go back and see if I can work in a soil temperature factor, but I haven't tested for that yet. But it's really just, you know, that's just a hypothesis based on the fact that it's typically northern states where we do see the decrease in predictability, and that typically happens, especially at the beginning and ends of, or actually, especially at the beginning of seasons, not so much at the end.